Today is March 7th, 2017. My seminar is Extreme Battery Trilogy. The abstract, so we may see a little bit bigger. Let's see. See a full abstract. Extreme battery may be defined as the battery has the highest power storage density, the fastest charging speed, and the fastest discharging speed, and highest battery efficiency. Compounds with the perovskite structure play an important role in battery materials. Once a formula of metal composition is decided, carrier defect may determine the power storage density. Charge carriers are either electrons or ions, or their vacancies or voids. When a material reaches its extreme defect while maintains its single crystal structure, it reaches its sealing storage volume. Charging and discharging resistance may be controlled by crystal domain size or grain boundary density. If the material forms a whole complete crystal without a grain boundary, the domain size is the crystal size. The resistance is minimized. I uploaded this video seminar presentation on LinkedIn. The first portion is processing ambient. The second is nano equipment, a combination of nano motion and high temperature sintering. The third and the last is nano epitaxy. This trilogy explains how to make the materials to their ultimate property limits in terms of equipment and processes. I enjoy the concept of extreme material, extreme performance. Behind the concept of extremity is perfection. So the first section is a processing ambient. I actually use a p-type perovskite as an example. The p-type perovskite, it really the materials you can consider as insulator, and actually depending on what are you doing, what are you going to use it for. So, but it does have some characterization for p-type, the semiconductor properties. That's why we use a p-type. Definitely you can use the n-type. I just use this material as an explanation here because we're doing for different applications. That's why the oxygen ions are the carriers for this case, but definitely it can be used for some different applications. But in the battery application, I think this one may not be. You may have n-type material. Carriers should be could be sodium ions, lithium ions, hydrogen ions, or other vacancies, right? Or electrons, whatever. Here I need to clarify this defect is not that defect. So what that means, really, okay, let's see the larger full screen reading. So this defect is not that defect. Really, that means we actually, so here probably vacancies or voids are more accurate. However, people, I actually, the time I started here, for this application, really I was new person. But the field in this application, they are used to have defect. Yes, but I prefer use vacancies or voids. You see, I said the oxygen is a carrier. Oxygen ions is a carrier in this case. But so that let's see, the perovskite is the name perovskites really represent, broadly speaking, really, you see the AbO3, the A is a group of metals, B is another group of metals. The reason the oxygen contents in this can be changed because of the multivalence metals. So broadly speaking, like either for lithium battery or sodium silicate batteries or some others, broadly speaking, they can all put it in the concept of perovskites, but maybe narrowly people prefer some specific oxides considered perovskites. Others they rather call some other names. But here I'm trying to really describe the how you increase the volume of the storage of your carriers. So you can definitely, broadly speaking, everything in metal oxides considered, the perovskites. Here you see how do we control the oxygen content in the AbO3. Definitely you can see you can reduce it to some much lower than 3, we sometimes call delta minus 3 minus delta. The delta is how much less oxygens you can have in the material. So what we control is that during the processing you can really reduce the partial pressure of oxygen in the ambient. So you see here, might be, I think this might be oxygen, pure oxygen. We use pure oxygen, and you may use air, or you may use nitrogen. Then we use a reducing ambient, and may use the hydrogen, some percentage of hydrogen in the maybe argon or helium or whatever. So to reduce the partial pressure of oxygen. Here, this one here is the log PO2. So here, you can see here, you definitely reducing the oxygen content in the material until here. You see here, sharply change, which we may not want to see because you want to keep the single crystal structure, but you want also the material really is a solid material, like a piece of material. If you then, when to reach this sharply change, really the single crystal crashed or collapsed. So then you may not have, and also the piece really like crashed piece, like powderized or something. So now here is X-ray diffraction patterns. We see really these two are the same, just under different log PO2. So you see here 1, 2, 3, they are still single crystal, but here we put them together trying to compare really for different, not your application for battery material, but we see when you change the ambient of processing, then the oxygen reduced, then you have the crystal have a deformation, or your lattice parameters change, like A, B, C, or alpha, beta, gamma change, then you see the shift of the peak, right? Shifting to this direction. That's the reason I put them together. And then when you see reach there, that's what we see, the last one we see. This one really sharply changed. The same thing here. Some peak disappeared, then you saw you can see the multiple peaks. It's really, that means you don't have a single crystal anymore. It's really crashed. So this X-ray diffraction pattern also, match what happened here. So then there's another, you confirmed, use this one to confirm that. Each formula has its certain limit to keep its single crystal structure while reaching its maximum vacancy volume, where it has a maximum carrier storage density. That's what we saw and we mentioned in the abstract. So here, because of application, we have a harder material. That means our composition of metals really different, maybe different from your applications. The harder, it's really not maybe not a right word, but I call it harder. Means the melting point of the material, the crystal really is much higher. So that's harder. So in your application, battery materials, either lithium battery, or for lithium battery, or sodium silicates or something, the melting point may be much lower, and that the material is much softer. That could be means your crashing content, the point of a crashing, you may have a much lower content of whatever you are trying to reach. So that means your vacancies of your carrier, or the voids, say, you can have a much higher volume of a storage than this material. I just use this material as an example. It's really not for your application. So here is another a measurement of thermal expansion. The same thing, but the reason we did that measurement really is for the materials for the application. The engineering design, so they may put this ceramic materials and the metal support or something together. So they need the data for the application. It may not exactly for your application. The same thing here. So we see that thermal expansion or percentage, linear percentage change, really not that big. This is a percentage. You see somewhere, from oxygen, air to nitrogen, and increase the hydrogen percentage to the lower partial pressure of oxygen. So the same thing here, it definitely crashed. That means it's really confirmed the before we said that at some point, definitely at which point really it's not exactly but we just measure the point by point. We do not continuity of it's really hard to do that. Definitely you can mix up different composition of gases ambient to do different measurement. But here it does confirm the conclusion we said before, right? The same thing here. Really, this is the what we got the first picture about oxygen content. Really, based on this one, we really measure the weight loss. Really, actually, how do we make that? We definitely cannot do the in situ measurement for all of those. Measurement. What we can do is we quench the samples, because at the high temperature and under that ambient, so when it we consider reach the equilibrium, so we can quickly move the sample to the much like ambient temperature at the normal temperature, like 20 degrees C or something. Quickly move that sample from high temperature zone into the cold zone. So then the sample is quenched at the condition, the structure maintained the structure when it was at the high temperature, and the oxygen content is also maintained at the level where when it was at a high temperature. That's the reason we definitely can. Of course, if you are able to do the in situ measurement, it definitely will be great. And also for the X-ray diffraction, see, our material really, for X-ray diffraction, we need to grind the material into the powders. So you definitely cannot do the in situ grinding, right? So whatever. So there are many other characterizations for different applications. For example, some people doing the neutron diffraction for magnetic structure analysis. Definitely we also have that data. However, I don't want to show it here. This is for different applications, not relevant to your battery application. However, I need to mention that what I'm trying to say, if you have you made some breakthrough in your sample for whatever applications, really your material maybe nobody else ever did. If you keep it with yourself, it may be a waste for the social resource, the resources for the whole world. If you can share, when I say share, really not you just give your example. You may also have a conflict of the interest or some other regulations. However, if it's possible in a quantified way, or this paid way to share your example to the other people, they may have a different purpose to study. Like here, you see, my interest, I do not need for application, I do not need the neutron diffraction patterns, but for some other people, they also have their specialties or their expertise in their areas, so they may need your examples for some further characterization from different purposes. If that's possible, but that I may have a different seminar to talk about it. So we said the first, you see the